Okay, so in this video, we'll be drawing regular polygons inside a unit circle using Python and Matplotlib. But before moving on, I want you to know some of the mathematical prerequisites that we'll be using in this video. So if you're not familiar with those, we may discuss it beforehand so you can follow along the video easily. So the first thing that I want you to know is the measure of each internal angle inside a regular polygon, which is given by this formula, n minus 2 times 180 degrees divided by n. This is the measure of each internal angle inside a regular polygon. The second thing that I want you to know is the cos theta sin theta definition of a unit circle. So let me draw a circle here. Yeah, I think that will do the work. And let me draw the axis. So this assume it to be a unit circle of radius 1. That's how we define unit circle. These are the axes. This is the origin, and the sin theta and cos theta definition is given like this. Imagine if we take this particular point and join it with the origin, then this, and if this angle is theta, then this length is sin theta and this length is cos theta. So you may define a circle as a locus of a point which satisfies this equation. So you may define a unit circle as a locus of point which satisfies this equation, sin theta plus cos theta equals 1, where for all theta belonging to this particular range from 0 to 2 pi. So you may define a unit circle as a locus of point which is satisfying this equation for all thetas belonging to this interval from 0 to 2 pi. This is what I want you to know, because this is the expression that we'll use to draw the circle in our Python notebook. Now we'll discuss the theory behind our polygon, of how we'll be drawing the polygon inside our unit circle. So let me draw another circle over here so as to show you what approach we'll be following. Let me make it a little bit bigger. Yeah, so I'm sorry. Yeah, so what we will be trying to do is, let me take a square. This is not obviously a square, but assume it to be one. So if this is a square, what we will do is we'll start from this point. This will be the common vertex for all of the regular polygons that we'll assume, and our aim is to calculate all the intersection points that the polygon has with the circle. Now how will we go about doing that? I'm sorry, this is the axis. So this is the origin, and this point will be the common point for all of the polygons that we'll be drawing inside the circle. Now the theory that we will be using is that our main aim is to find all of these coordinates, all the vertices of our polygon, and then we'll use the plot functionality of our Matplotlib library to connect all these points by the line. So if we know the equation of this line, of this particular line, then we'll able to calculate the intersection point with the unit circle, the intersection point of the unit circle with this line, and if we know the equation of this line, then we'll able to calculate this point, and if we know the equation of this line, then then we'll be able to calculate this particular intersection. So what we will be doing is we will rotate, for every polygon we'll rotate a line about this point, about this particular point. We'll rotate the line for every polygon. We'll rotate the line to calculate all of the intersection points for the polygon, and it will start by this angle. Now what angle is this? This angle, the starting angle will be whatever the internal angle is divided by 2, the half of internal angle. So if this angle is say alpha, then this angle theta will be alpha by 2. So the first line, the first intersection point is very easy to calculate. This particular intersection point is very easy to calculate, as we know one of the points and we know the angle. For every polygon we'll be knowing the internal angle, which is this angle. In case of square it is 90 degrees, but for every angle we can calculate, for every polygon we can calculate the internal angle using the formula that I have just shown you above. And we will divide this formula, we'll divide this particular angle by 2 to get this angle, the theta angle. And when we have the angle, this particular theta, and we have a point, we can draw a line. So using this angle we can write the slope of the line will be given as tan theta, and this particular point will be this particular point is nothing but the x coordinate is -1 and the y coordinate is 0. So all of the lines that we'll be using to calculate the intersection point will be rotated about this point. All of these lines, this will rotate like this for specific angles. Firstly for this angle theta, then some angle will be subtracted and the line will rotate like this to get to this angle, which is 0, and then some again the angle will be subtracted to get to this angle, which is nothing but minus theta. If this is so in case of square, theta will be 45 degree, so this will be minus 45 degree, right? This angle will be minus 45 degree, this angle will be minus 45 degree. So if we have the angle, so we have the angle, we can calculate the slope of the line, and we have the point. So using point slope formula, if you know the point slope formula, that is given by y is equals to mx plus c. If you know the point, slope, this is the intercept form of slope intercept form. The point slope formula is given by y minus y1, y1 minus y is equals to m times x1 minus x. This is how we give the this is the point slope formula of a straight line. So so here we'll put y1 as -1, I'm sorry, here we'll put y1 as 0, x1 as -1, and slope as tan of 45 degree for square, tan 45 degree, right, for this particular line. And for this we'll rotate the line by we'll subtract 45 by 45, so to get the angle 0. Then we'll get to this line, this particular line that we have, and then we'll again subtract minus 45, so to get to this angle minus 45. So we are moving from 45 to 0 to minus 45, right? Now this is the thing that we will use to this is the formula, this is the formula, this is called the point slope formula. This is called the slope intercept form of a straight line. This is the point slope formula of point slope form of the straight line. This is what we will use while drawing this polygon. Now let me take another polygon so as to show you how the most critical part of this the most critical part of this particular code will be to find the delta theta. How much rotation will this line have to make at each turn, so to get the correct intersection points. I mean, it can't be rotated at by this much factor, otherwise if it gets rotated by this much factor, then we'll get the intersection point over here. We want it to rotate by a perfect angle so that we can get to this line, so as to get this intersection point. Then it has to rotate by some certain constant factor, so that we can get to this line to get this intersection point. So this is so the angle by which it will rotate, I'm calling it delta theta. So this is the angle of rotation, how much rotation the first line will have to make, because the angle, the theta for first line is very easy to calculate. It is nothing but the internal angle by 2, right? The first line's slope is very easy to calculate. The lines that follow after the first line, the slope for those lines are very hard to calculate, and that is what we'll focus on, and that is what we'll try to generalize in the next portion of our discussion. So let me clean the whiteboard a little bit so that we can I'm so sorry for the interruption. Actually, my mom came into the room, which disturbed the which disturbed the flow of the recording. So I'm so sorry for the interruption. I actually forgot the checkpoint of where I had left. I think I was taking another illustration about of another polygon, I guess, right? So let me clean my whiteboard a little bit. Yeah, and let me take another polygon. Yeah, so let me take a pentagon which will be drawn like this. Assume it to be a regular pentagon. I know I know it won't be perfect, but just for the sake of recording, just for the sake of drawing, and just for the sake of showing, so assume it to be a regular pentagon. Okay, so our aim is to, so this angle is very easy to find, and we'll be able to this angle, and therefore this particular line is very easy to find. This particular line is very easy to find, and because this angle is nothing but the internal angle divided by 2. Now if we join all these lines, like this, and this particular angle, the last side of our polygon is also very easy to find, because this is the negative of this angle, the above angle. So this is nothing but minus internal angle by 2. Now what we the thing that we will have to take the most stress on is to find these angles. So what I want you to think about in this particular case is all these lines are equal, because it's a regular polygon. So all these lines are equal, right? All these lines are equal. Even these lines are equal, right? So the angle opposite to this line, and and the angle opposite to this line, these angles should also be equal. And if you want an intuitive picture of what I have just said, then imagine that you have a piece of paper in the shape of in the shape of a regular polygon, okay, and you're drawing and you're making an airplane. So what I'm saying is, if you rotate if you rotate this side of the paper, this particular side, if you rotate this particular side of the paper in this direction, or if you rotate this side of the paper about this line, if you rotate this side of the paper, the upper side of the paper, like this, then you will be left with a structure like this, right? So this side is rotated and being and that is overlapped onto this side, and if the overlap would not be perfect, I mean, if this side would have been bigger, then angle would not have been angle would remain the same, right? If I extend this side like this, then angle would not change. This angle would remain the same even if I extend this side. The only way the angle can change is when I extend this side. If I extend this side, then this side will also have to follow, and this angle will be changed, right? So if you rotate this side, if you rotate the upper side onto this base, over this base, then you will get a structure like this. And let's rotate this side, the lower side as well, onto this side, onto the lower base, and then we'll get a structure like this, a triangle, right? So these two sides are being let me draw it with another color. So these two sides are being rotated onto the lower base. So if this angle would be different, then the side would not perfectly overlap. It would go somewhere over here or somewhere over here, right? But in case of a regular polygon, the sides completely overlap. You can try it if you have craft paper, if you have any useless paper in your home, you may try it in your home as well. That if the, let me center it so that you can see, so that you can see that if the sides would be bigger, then it would not overlap completely, right? On either of the sides. So if this side would have been bigger, then it would come out like this, or if that side would have been bigger, it will come out like this. But in case of a regular polygon, if you will rotate this particular side onto this triangular base, it will overlap completely. So this is the upper part that we have rotated from that side like this. And because this angle overlapped completely, therefore we can say that the angles are equal, right? Therefore we can say that this angle is equal. This is a more intuitive picture that you can also experiment with in your home. The overlapping thing that I have just explained, or if you want a more mathematical or concrete picture, then you may assume it like this. You may assume it like the statement that I've made before explaining this intuitive picture, that the angle opposite to these sides, which are equal in length, they must be equal as well. So what we have to do is we have to divide this angle the internal angle into 3 equal parts. Okay, so we have to divide this internal angle into 3 equal parts. Now the internal angle of a pentagon is 72 degree. Now we have to divide it in 3 equal parts. Okay, so let's take a square and see how many divisions do we have to make in that polygon. So imagine it to be drawn inside a unit circle. I'm not actually drawing the unit circle. This is the angle, and these are the points that we have to get to. So in this case, we have to divide the internal angle, which is 90 degree, into 2 equal parts. The first one is the known quantity, is the known angle. Then we have to rotate it by some angle to get to this line. Then we have to rotate it by some by that same angle to get to this line. And same is what we are doing over here as well. In this case, we know this angle, the angle or the theta for this first line is known. We have to rotate by some angle to get to this line. Then we have to rotate it by that same angle to get to this line, and we have to rotate it by another angle by that same angle to get to this line as well. So in this case, we had to divide this angle, the internal angle, into 3 equal parts. In this case, we have to divide the internal angle into 2 equal parts. Now the observation that I made when I was thinking about this problem is that when you have a 5-sided polygon, then you are dividing the internal angle into 3 equal parts. And when you have a 4-sided polygon, you are dividing the internal angle into 2 equal parts, right? And let's take the simplest polygon, the triangle. And in this case, this angle will be known, and you have to just you do not have to make any division in this case, because this angle and this angle are already known. So you don't have to divide this line divide this angle at all. Just rotate this angle, the 60 degree, which in this case this angle would be 30 degree. If you'll draw it in a unit circle, just rotate this line by minus 60 degree. In this case, you don't have to divide it in any you do not have to divide it at all. You do not have to divide it at all, because this point, there are only 2 points, right? And both of the angles are, you know, that this is minus 30 degree. For this point, the slope's angle will be minus 30 degree, and for the above line, the slope's angle will be 30 degree. So you don't have to divide it at all. Just rotate the angle by minus 60 degree and you'll get to the second point. So in this case, you had to make no division, right? Or you can say that you made one division, which means that the 60 degree remains 60 degree. So I tried this out. I tried this pattern, and I found that this pattern came out to be true. That is, for every n-sided polygon, you have to make n minus 2 divisions of your internal angle. For every n-sided polygon, you have to make n minus 2 divisions of your internal angle. Now this is purely observation based, because when I was solving this problem, when I was thinking about this problem, I tried to solve it in many ways. I tried all sorts of ways to draw a polygon inside a unit circle, but this is one of the patterns that I came across. This is one of the patterns that I observed. I don't know if there's any proven mathematical form of this fact, because I have not studied these kind of things formally. This is just completely observation based, which I observed when I was solving this problem. I don't know if there's any formal proof or there's any formal way to define whatever I have just explained to you, that for to calculate the intersection points, you have to make n minus 2 division of the internal angles. So to get this particular factor by which the rotations will be made, by which the lines rotations will be made. So I don't know if this is a proven fact. You may comment in the comment section below about if you know anything related to this particular observation that I have made, because I don't know if there exists any formal proof of this observation or not. But yeah, this is completely observation based, and this is completely this is just a fruit of my mind. I don't know. I didn't knew at that time when I first observed that it'll be so general, because when I made the program, it was able to draw polygons of all this, of any side that I gave it to draw without any problem. So it came out to be more general than I was thinking. I actually tried it on just four or five polygons, and I just generalized the result, and I tried to create the program, and it worked. This is what happened in my case, and this is what I'm explaining. Then how I explained myself, the theoretical reason behind what I was doing. So this is the theoretical reason that I have explained myself to when I first created the program, and that is what I'm explaining it to you as well. So enough of theory. I think this is enough, and I think I've just explained you what we have to do. We have to divide the internal angle into number of sides minus 2 divisions. N minus 2 divisions. We have to divide the internal angles while in this particular. We have to divide the internal angles by this factor, n minus 2 factor. N is the number of sides. Okay, so something strange happened actually while I was recording the video. The recording actually stopped suddenly, and I didn't realize that. I realized after I finished my explanation, along with writing all of the code, when I opened the software to stop the recording, I realized that it was not recording at all, and only the first 27 minutes were recorded of my explanation. That actually pissed me off completely. So just by anger, I deleted all of the code that I written and the previous video as well. So I don't have the strength left to actually re-record everything else, and write all of the code again. So what I'll do is I'll complete the mathematical prerequisites that are left, and after which I'll discuss the code that I have written already, about how those mathematical concepts that I have discussed are going to apply to make the polygons inside the unit circle. Okay, so let's complete the rest of the mathematical prerequisites that are left. Now, the last thing that we discussed was that the internal angles are divided into this factor. So the internal angles are divided into n minus 2 divisions, right? Are divided by n minus 2 factor, right? So this is the internal division that we do for the internal angles, right? This is the factor by which we divide the internal angles by n minus 2, sides minus 2. Now the other thing that I want to discuss is the general equation of the line about this point. Now if you as I've said before, that the line using which we'll calculate the intersection points of our polygon will rotate about this point. This point is minus 1 comma 0. So the general equation of the line for any theta, for any m, for any slope can be given as, we'll use the slope intercept for a slope point formula to calculate the general equation. So y minus y1 is equals to m times x minus x1. So this is the general equation of the line that we will use, and if we substitute this coordinate into this equation, then we'll get y is equals to m times x plus 1. This is the line, this is the equation of the line which is rotated about this point for any m, for any value of slope. This is the general equation of the line which is rotated about this point minus 1 comma 0. Now as we have to calculate the intersection point, we have to solve the equation of the line and the equation of the circle simultaneously. Now for a unit circle, the equation of unit circle, which is centered at the origin, it is given as x square plus y square is equals to 1. Right? Now we have to solve these two equations, the equation of the line and the equation of we have to solve these two equations, the equation of the line and the equation of the circle, simultaneously. For a fixed theta, for a fixed m, say the m is fixed, so for a fixed m we have to solve these two equations to find the intersection point. Then we'll change, then the m will be changed, then again we'll solve these two equations. So we'll use actually a loop to do this task for us. So now we'll find the resulting intersection equation. So for that, what we'll do is we'll replace y from the equation of the line, we'll replace y from the equation of the line, or we'll substitute y from the equation of the line into this equation of the circle, and it will become x squared plus, if we'll replace y in this place, then it will become m times x plus 1 the whole squared minus 1 equals 0. Now the other mathematical prerequisite that you need to know is related to the position of a point with respect to circle. Now as you must be knowing that any point lying on the periphery of the circle, lying on the boundary of the circle, the coordinate of that point, if substituted into the equation, if substituted into the equation of the circle, will satisfy the equation, right? That means x squared minus y squared is equals x squared minus y squared minus 1, x squared plus y squared minus 1 will be equal to 0 for all of the points on the periphery of the circles, for all of the points on the periphery of the circle. So for all these points, if you substitute the value of x and y into the equation of the circle, you will get the value, the resulting value will come out to be 0, right, from this equation. Now if you will take any point that is outside the circle and substitute in this particular equation, and substitute its coordinates in this particular equation, in the equation of the circle here, then the value will come out to be positive. And if you will take any point which is taken inside the circle, substitute its coordinate into this equation, then into this expression, then the value will come out to be negative. So any point which is taken inside the circle, x square minus y square minus 12 will spit out a negative value if the point is taken inside the circle. X square plus y square minus 1 will spit out 0 if the point is lying on the circle, lying on the periphery, and if the point is lying outside the circle, then this will spit out a positive value. So these are the conditions that we will use actually in our program to distinguish the points, to distinguish all the points which is lying inside the circle, and the point which is lying, and the intersection point, and the point which is lying outside the circle, because we don't care about we don't care about these points and these points, but to get to this intersection point, we will have to make use of the given conditions that I have just written down here, we will have to make use of these conditions in order to get to the intersection point, because most of the time we will be having the value coming out to be negative. Why? Now I will discuss the I will discuss the approach, then you'll understand why most of the values will come out to be negative. Now our journey will start from this point, -1, 0. We'll start from this point for every line. For every line we'll start from this point, and we will move in the positive direction of the x-axis like this. We will make small incrementations, and at every incrementation, at each step, we will check the value of x in this particular equation. We'll substitute the value here in this particular equation, in this particular expression, I'm sorry, in this particular expression. Let me write that down separately. So x squared plus m times x plus 1 minus 1, this expression, we will substitute each of the value after incrementation. For example, after the first incrementation, we got to this particular point, or after some certain incrementation on the x-axis, we got to, wait, my cursor just disappeared. Yeah, so yeah, we got to this particular point. So we will substitute the value of x coordinate of this point into this equation and check if the value is coming out to be 0 or not. If the value comes out to be 0, then we will append that coordinate into our list of vertices of our polygon. And if the value is not coming out to be 0, if the value is coming out to be negative, which in this case it will, because for this particular point the value comes for this particular point, the point on the line is coming inside, the point on the line is coming inside the circle. So if we'll satisfy the equation for this point, if we'll satisfy the equation for this point, so if we'll satisfy the equation is for this x coordinate, then we will get this point on the line, right? This is the resulting coordinate, this is the resulting point on the line with respect to this x. So with respect to this x, we have this point on the line, and if we will satisfy this line onto the equation of the circle, the value will come out to be negative. And if the value comes out to be negative, then we have to make another incrementation and then check if the value is coming out to be 0. If the value again comes out to be negative, we'll make another incrementation, and we'll keep making incrementation on the x-axis till we get to a point where we hit that 0 mark, where the value after substitution of this x coordinate, for example, in this case, we are for this particular x, for this value of x is equals to 0. For x is equals to 0, what I'm sorry, yeah, for x is equals to 0, for x is equals to 0, if we'll substitute that value into this equation, the value will come out to be 0. Why? Because for x, after keep making incrementation, if we get to this point x equals 0, then corresponding to this point, the point on the line and the point on the circle, they are intersecting, and this is what we want, right? This is the intersection point that we are looking for, the point where line and the circle intersect. So at this point, we will append this value into our vertices list that we have made for our polygon. So this process of keep making incrementation will happen up and until we get an intersection point for our line, for that slope, for that m. And the moment we'll get that intersection point, we'll change this m, we'll rotate this line, and again this process will start from -1 0 -1 comma 0, and again we'll keep making incrementation until we get the other intersection point. After we'll get the other intersection point, this m will again change and the line will rotate, and again this process will start from the beginning, and this process will continue until, so we have to run two loops. The first loop is the incrementation loop and the second loop is the rotation loop. So the incrementation loop will stop in two cases. The incrementation loop will stop either after having all of the incrementation. The incrementation loop will stop after so there are two breaking points for the incrementation loop. The first one being that if you hit some x for which the value comes out to be positive from the equation, right? As I have discussed, that any point that is taken outside the periphery of the circle spits out a positive value from the equation. So this equation will spit out a positive value for this x, or for any x for that matter coming after 0, right? So in this particular case, so what will happen is that this equation will spit out a positive value, and if the equation spits out a positive value, we'll break the loop. The second breaking point for the loop is after having all the incrementations, if the loop hits this 1, 0 mark. If the loop hits this mark, this particular mark, 1, 0 mark, so if it hits this mark, 1, 0 mark, then there is no point in actually getting further, right? Because we'll eventually get out of the periphery of our circle, out of the boundary of our circle. So the moment we'll hit the periphery of the circle on the other side, that is we reach the 1, 0 mark, we will break the loop. So the incrementation loop will break at 2 points. If this particular equation spits out a positive value, that is if the point gets outside the periphery of the circle, then this loop will break, the incrementation loop. And the other breaking point of the loop is when the incrementation itself gets out of the periphery of the circle. I'm so sorry for the interruption. I can't explain the situation right now. I mean, actually, there are many disturbing elements in and around my home which who break the flow of my explanation and recording. So that's why I had to pause. That's why I have to pause repeatedly in order to record this video with a clean voice. So yeah, where were we? Yeah. So there are two breaking points of the loop, of the incrementation loop. Either when in the first case, if the point itself gets outside the periphery of the circle, and in the second case, if the incrementation itself gets to the other end of the circle, then there's no point in calculating for values greater than 1, 0, because they'll obviously be outside the circle. So we'll break the loop in that case also. So these are the two breaking points of the incrementation loop. Now we have to rotate these lines as well up and until we satisfy some condition, and the condition that I'll be using is that let me make some space and let me make another circle here as well, so that we can work with a more cleaner circle. Obviously this is not a circle and this is obviously not a line. So yeah, we'll be using the fact that let's say it's an n-sided polygon which has obviously n sides, any arbitrary number of sides, but the one fact remains constant. The fact is that the first side, the angle that the first side makes with the x-axis will be negative of the angle that the last side makes with the x-axis. first of all, whatever this angle will be, it will be bisected by the x-axis, right, in the unit circle. And after this bisection, these two angles will be equal. And after the intersection points of first line, after the intersection points are calculated for the first line, some angle will be subtracted, right? Then we'll get another line. Then after numerous amount of subtraction, after subtracting by n, after subtracting the angle by n minus 2 times, right, we'll subtract, because we have divided this region into n minus 2 divisions, so n minus 2 sections. So we'll have to subtract theta by theta n minus 2 times. So for each rotation, we will subtract theta by some delta theta, and the delta theta will be subtracted n minus 2 times from theta. So after numerous amount of subtractions, you will get to this angle. The last angle will be minus theta, right? Because this will be measured clockwise. This angle will be measured clockwise, and this will be measured anti-clockwise. So if this is theta, then this is obviously minus theta. Then therefore the breaking point for this rotation loop will be this fact, up and until the loop will run until theta plus this minus theta, whatever the theta is, the sum of these two becomes 0 or very close to 0, as a matter of fact. So yeah, we will get new theta for after every subtraction, right? After every subtraction we made, we'll get new theta, and after we will get so after the calculation of each new theta, we will check this condition. If theta plus this particular theta, I mean if the summation of these two angles, let's call it alpha. So if the summation of these two angles are 0 or not. So after the intersection calculation for each of the line, delta theta will be subtracted, and after the subtraction we'll check this condition. If the summation comes out to be 0 or nearly 0, we will break the loop, and if not, we will not break the loop. Again the loop will be run and delta theta will be subtracted, intersection points will be calculated, and again after subtraction we'll check this condition. So after all of those subtractions and after at each checkpoint we'll check the condition. When we'll get to the last side, this condition will become true. Theta plus alpha will become 0, nearly equal to 0, will become 0. Then we'll break the loop. Then this rotation loop will be broken. Then the rotation loop will be broken. I'm sorry. Yeah. Then the rotation loop will be broken. Here. I'm sorry. So yeah, then the rotation loop will be broken. So these are the two loops, the rotation loop and the incrementation loop that we will run. So in totality, what will happen? We will fix the theta, call the incrementation loop, calculate the intersection points, then we'll change the theta. After we'll change the theta, we'll call the incrementation loop again, calculate the intersection point, after which we'll change theta again. So we will call this incrementation loop for each of the thetas, and up and until this condition is met. And the moment this condition will be met, we will be having all the coordinates, all the vertex coordinates that we need. Now there is a problem in this approach. The main problem is that we are always starting from -1 and 0, right? So it will be like for the first line we have -1, 0 and this intersection point, Then again we'll have -1 comma 0 and this intersection point, and so on and so forth. So what will happen is that in the list we'll be having this particular point with a repeated this particular point will appear in a repeated pattern. So we'll have an intersection point, then we'll have again this point, then we'll have again another intersection point, then we'll have again this point. So this point will be at every alternate position in our vertices list. So we have to perform some cleaning as well to remove this point, so that we can remove this particular point which is appearing on our list on a repeated basis, because we don't need this point, we only need the vertices, right? Otherwise what will happen is that if you'll not perform cleaning, then the matplotlib will interpret your list as it will not interpret your list as a list of as a list for coordinates of a polygon. It will look something like this. It won't look like a polygon. So if you want it to look like a polygon, then before giving it to the plot function, you must delete the repeated value of this particular point, so that after this point it does not come to this, and then after this point the plot functionality does not come to this point and then go to this point. Rather avoiding this bridge, rather it should avoid this bridge and go to this point directly, so that it can draw the polygon. So we'll have to do this thing as well, the cleaning part, because we are, for every line we are starting from this point only. Therefore before every intersection point we'll be having this point. So this point will be appearing on a repeated basis. So we'll have to remove this point, so that the plot functionality does not interpret this point as a bridge before moving on to the next vertex. Instead we'll remove this point and surpass and bypass this particular bridge and go to this other vertex directly. So that's it. This is the mathematical prerequisite that was needed to make the regular polygons inside the unit circle. Now I will open my Jupyter notebook to show you all of these concepts and and their applications in action. So let me open my Jupyter notebook to show you that. Here I have opened my Jupyter notebook, and we'll discuss each and every line of code here, so that you can understand that how all of the things that we have discussed are being applied in this case. So as you can see, the first thing that I have done is imported all of the libraries that I'll be using. NumPy obviously is a very important library for scientific computation purposes, so NumPy is a must, and matplotlib for polygon, for obviously the for using its plot function, so that we can plot. So matplotlib is the plotting library that we'll be using, visualization library, I'm sorry, that we'll be using. Now in this particular line, what I'm doing is I'm using the linspace function. So linspace function, what it does is it creates it gives you a set of values. Means it gives you a set of values between in an interval. So for example, so linspace function, what it does is, for example, let's say if you have an interval from 1 to 2 closed on both sides, and you want 600 values in this particular interval, so you can use the linspace function to get a linearly spaced values, and that's why it is called linspace, because all of the values they will be evenly spaced, even though it doesn't matter how much small interval that you give it, but the values that you will get after this function, after applying this function, all of those values will be linearly spaced. That means all of those values will be uniformly spaced. So this is what linspace function gives. Linspace is linearly spaced values. So if you ask me, the literal meaning of what linspace does is, and NumPy's linspace function, it gives you linearly spaced values between or in the given interval of start comma stop, closed on both sides. Because if I don't think I have run I've run all the cells, so let me run all the cells as well, and then we'll see. Yeah, so let me open. Okay, so the kernel is busy, just wait for a second. Yeah, all of the cells they have ran, and these are all the coordinates of the vertices. And yeah, so here is the quick documentation of linspace function. As you can see, here's the start, stop, and the number of values do you want, the number of linearly spaced value you want. You have to specify that. For example, in this case I have specified 747, as I like odd numbers, so I have specified the values to be 747 between 2 and 3.14. so it is nothing but pi. So so I wanted the value for angles, right, to calculate, to draw the circle. To draw the circle in the first place, we need some angles, right? So the circle covers a angle of 2 pi radians. So I wanted the angles, so I wanted the values from 0 to 2 pi, 2 times 3.14, and so I want, and because I wanted to draw a very smooth circle, that why I have chosen this much values. If I reduce the number of values, then obviously a hazy circle would be drawn, and because I have chosen this much values, therefore for all of these values the sine theta and cos theta are calculated. So we'll use the sine theta cos theta definition for circle, for drawing the circle. So in this case we are getting 747 values between 0 and 2 pi, and this is the value that we are using in calculation, in drawing the circle. So here I have so in this, here you can see the circle. Here I'm drawing the circle. So I'm using the NumPy's cos theta functionality for all the x's values, and for all the y values I'm using the NumPy's sine theta functionality. As I have discussed, that you can think of a circle as a locus of a point satisfying the equation sine theta plus cos theta is equals to 1 for all the thetas ranging from 0 to 2 pi. I've used the exact definition to calculate this to draw this circle, sine theta cos theta, and here is our angle ranging from 0 to 2 pi. So this is how I have made my circle. Now I have made a function called polygon, which takes in sides as its input, and it spits out the x coordinate and the y coordinate of the vertices as an output. So these are all the variables that I have used. Some of the variables are also the ones that I have not used actually, but I've just defined it. For example, the internal angle in radians, I have just defined it for the sake of defining it. I mean, just because I wanted to use the degree to radian function. That's why I defined this variable, but I have not actually used it in the function itself. So initial x is our starting position, the starting position for all of our lines, right? This is the starting position for all of our lines, right? This -1 point, -1 comma 0 point is our initial x. For each of the line that we'll have, we will start the incrementation process from this point only. So initial x is a constant, obviously. That's why I've defined it to be -1. All these x and y values are the list that will be returned at last. Then the internal angles, as I've discussed, this is the formula, sides minus 2 times 180 divided by the number of sides. And I've converted all this internal angle into radians as well, np dot by using the degree to radian method of NumPy library. Then this is the initial angle of the first line. So as I've just told you that the first line, the angle for the first line is very easy to calculate, right? The angle for the first line is very easy to calculate because the first line will be having the will be at an angle theta by 2 from the positive direction of x-axis. So this is the initial angle. This is the starting angle that we have for our first line. So this is the initial angle theta, internal angle in radians by 2. Okay, so I have not actually used the internal angles variable. I'm actually using the internal angle in radians variable. So yeah, delta theta is the angle by which the first angle will be subtracted. Okay, so this is the subtracting factor. As I've just told, as I told you before, that it will be this particular internal angle divided by this internal angle divided by n minus 2. They will divide it by n minus 2 factor, right? So that is how I have calculated. I'm sorry. Yeah. So that is how I have calculated the delta theta part, and these two values are actually equal. In the initial case, I have made it equal because I won't be disturbing this initial angle theta as we'll move into the further parts of our code. We will be manipulating this new theta value. This will be the value that will get manipulated. This will be a constant. The angle that is made by our first line will be a constant, and we will treat this value, and we will manipulate this value for the rotation purpose. So rotations will be made using this new theta value. That's why the initial values for both of these variables are same. Internal angle in radians by 2, internal angle in radians by 2. Because the rotations will be made with using this new theta. Now if you're asking why I have made this distinction, because in the last part I will use this constant to write the condition that I have discussed in the theoretical part for the rotation loop. Okay, that's why I have made it a constant. Now we will define a tool, the intersection loop, or what I discussed with you in the theoretical part, which is the incrementation loop. So this loop will run while this condition is true. So up and until the value of x, so the x is nothing but from where you want this loop to start calculating or to start incrementing. So if for any value of x, it can start from any value of x. If you want the loop to start from this value of x, it will start incrementation and calculation of it will start the incrementation and calculation of intersection points from this point. And if you want it to calculate from this point, then it will calculate from this. So you can specify which point do you want to start from, but obviously we'll start from the initial x. So in here, as you can see, in the rotation loop, I have specified the x to be initial x, that is -1. So it will start from -1. Okay, so this is the only input that it will take. So again, it will run only if the value is not equal to 1. So this is one of the breaking points of the incrementation loop that I discussed. It will only run if the value is less than 1 and it is not equal to 1. So by any case, if after the incrementation we surpass the value of 1, then then for that case I have defined this additional condition, that if the value is greater than 1, then break the loop. And here is that equation that we discussed. If you remember, this x squared plus m times x plus 1 the whole squared minus 1, x squared plus np tan theta is the m part. M is nothing but, obviously you must be knowing the m is nothing but tan theta. The slope is defined as tan theta, times x plus 1 the whole squared minus 1. So here as you can see here, we're using the new theta value. We are not disturbing this theta value. So obviously the first line that we are dealing with is using this new theta angle, the internal angle by 2 angle, as it's in its slope, right? np dot tan of new theta, right? So if it is less than 0, that means if this equation, the value of this equation comes out to be less than 0, then obviously we are inside the circle. So we'll make the incrementation. This is the incrementation process. X is equals to x plus some value, 0.0001, whatever it is. And if after this particular bit of code is for the cautionary purpose, that is if after the incrementation the value becomes 1 or greater than 1, then we will append 1 and 0 to our x and y values. Now you have to understand in what case it will happen that after the complete incrementation from -1 to 1 will not get any intersection point. This will only happen in case where the line becomes completely horizontal, the tan becomes 0, right? Because for every other line, you will get the intersection point before hitting this one part. Now for this particular line only, which is completely horizontal, lying on the x-axis, for this line only you'll have to move from this point, from this end of the circle, all the way to the last value, that is 1, 0, to calculate the other intersection point. Because other lines and lines that is not horizontal, you will definitely get the intersection point before hitting this one part. But for before getting onto this point 1, 0. But for this horizontal line, you'll have to move from this point to this point, from this end, from this particular end to this particular end. This will only happen in case when you will hit this horizontal line. Otherwise, all of the lines will get their second intersection before hitting this 1, 0 part. Okay, so this is what it is. That's what I'm saying, that if in any case you get to the situation where the x value becomes 1 or greater than 1, that means you're dealing with the horizontal line for sure. Then if you're dealing with the horizontal line, then if we know that we are dealing with the horizontal line and the second intersection point has to be 1, 0, then just break the loop and append these values. because we know, because if we're dealing with the horizontal line, then there's no point. If we know what the line is, then we know what the intersection point is. So just break the loop and append these 1,0 values. And this part is interesting because the second part is interesting because in the elif part, what we are doing is we are checking if we have any intersection or not. So this is the incrementation part when we were inside the circle. And in the second case, we are checking the intersection actually. So what we are doing in this case is I could have written this value to be double equals to 0, right? This is the condition, right? That this is the condition that I just discussed with you, right? So if this particular equation, if it is double equals to 0, then we are at the intersection. But you have to understand that we are dealing with approximations here. We don't know what value will be spitted out by this np.tan function, and that value will completely cancel out with 1 or not, because this value, let me use the whiteboard, because this value has to be equal to 1, right? Then only 1 minus 1, this minus 1 will be equal to 0. We don't know if this value will completely be equal to 1. Maybe this value becomes 0.99 or something like that, or 1.001 or something like that, because we are using the tan function. We don't know what kind of float and with how much precision we'll get the value. So that's why we are using this very small interval for checking. If the value lies between this interval, that means the value is very close to 0. Then we can assume that we have hit the intersection point and we can append the value of x. Now to append the value of y, what we will do is we'll use the equation of line. Okay, appending the value of y. How we'll append the values of y? We'll use the equation of line for that. Now if we have I think there's just too much mess in this part of the whiteboard, so let me use another color. So here it is. So if we get to this point, if we get to this point and we know what the x is, then we can use the equation of the line to calculate the y value. This is the y value, right? To calculate the y value of the of corresponding to our x, so that we can get the complete coordinate x comma y, right? We'll use the equation of the line that we calculated. This is the equation of the line, right? We'll substitute the value of x in this equation. Y is equals to some x. M is fixed. We know what the m is. For each of the theta, we know what the theta is, right? Before knowing the theta, we won't be able to access this incrementation or intersection function that we are making. So we'll substitute this value here and say x1, and then we'll able to calculate the value of y. So if we calculate this value, then we'll be able to calculate the value of y as well. So that is what we're doing. This is nothing but m times x plus 1, which is here as well. M times x plus 1. So this is how we are calculating the y value, np.tan nu theta times times x plus 1, and we are appending that value to our list. Okay, and here we are making another incrementation. So again, this will be checked actually if the incrementation is getting more. If the incrementation value is greater than, or if it has gotten greater than 1 or not. If it is, then obviously the loop will be broken down. And even if it is not, Then in the last part, there are only three cases, right? If it is equal, if it is less than 0, if it is equal to 0. So in the first if, we have defined the condition where the point is inside the circle. Okay, so the value will come out to be negative. In the second if statement, I have defined the condition to be equal to 0. The value will come out to be nearly 0, right? For the last case, the else case, the thing that is left is when the value comes out to be positive. So let's say if after the incrementation, that is what we discussed in the whiteboard as well. If after the incrementation, the value from this equation comes out to be positive, right? If the value comes out to be positive, then the loop will break. This is the condition that is left. That's why I have not specified it explicitly, because after these two conditions, only one condition is left, right? So so the loop will break if the incrementation causes the equation to become positive. If the equation becomes positive, then the loop will break. Now this loop is obviously returning nothing. It is just there for the amendment of values in the list. So it returns nothing. It returns no value, right? It just appends. It just manipulates whatever which is there, and that is the work of this function. It is not returning any values. Now we'll get to the rotation loop part. So this was our incrementation or intersection calculation part. Now this is the actual function or actual usage of this particular function that we have defined. This particular loop will run up and until this theta, this sum theta plus new theta is greater than 0.01. Now you know that this new theta will be the one to which we will be making the manipulations, right? So this is the theta from where we'll be subtracting the delta theta, as you can see. So after some point it will become negative, and after some point it will become negative of theta, as we have discussed that when we'll get to the last side of our polygon, this new theta will come negative of theta. So their summation will obviously be very close to 0. That is, it will become less than 0.01, and the moment this condition becomes false, this loop will stop, right? And this loop will only run up and until their summation is greater than 0.01. The moment they become very close, together, and the summation becomes less than 0.001, then this condition will become false and the loop will stop. This is how the for loops are run, right? We write the running condition. In what condition the loop should be running, right? So up and until this condition is true, the loop will run, and the moment it will become less than 0.001, when they'll come very close to each other, then obviously the summation, because one will be positive and other will be negative of that positive number, right? If it's like 2, first will be 2 and the second will be minus 2. So 2 plus minus 2 will be 2 minus 2. So even if the second one is not minus 2, it will be very close to minus 2, because obviously as I have said that we are dealing with approximation, so it will be very close to minus 2, right? So their summation would be very close to 0. It will be definitely less than 0.001. So in that case the loop will stop. Okay, if this condition is not true, if this condition is true, if theta plus new theta, that is greater than 0.001, that means they are not very close to each other, they are still significantly far apart, and initially they will all obviously be same. In the initial case, in the first case, theta plus new theta is also theta, so it's just 2 theta, right? So if it is 45, then in the first case new theta will also be 45, so 45 plus 45 will be 90, right? So in those cases the loop will run. So for every new theta, that we have, new theta. For every new value in the new theta that we have, we are calling the intersection function, and we are providing it the initial x value, right? We are saying that start the incrementation from the from -1 point, and then we are after in this case, in the second line of code, we have got the intersection points, right? So after calculation of intersection points, we are saying that the new theta is equals to new theta minus delta theta. That means here we are making the rotation. Here is the rotation part. Now if you look closely, if the new theta and theta, if they come very close to each other, then the point corresponding to then the intersection point corresponding to the last side won't be calculated. So if this condition holds true, that is, if theta and new theta, if they really become less than 0.001, in that case this loop will stop, but this conditional statement will be executed, right? This is the condition that I have provided. Then calculate then I have calculated the intersection point for that last line. And because if I had not written this particular line of code, then theta plus new theta, then the line corresponding to the minus theta value, you know that the new theta will become negative of the theta value. So in that case the loop will stop and the intersection call would not be made, right? Because at the moment this condition will come false, this call would not be made. So the intersection point would not be calculated for the last side. So that I am doing it here explicitly, because the moment this will, and after this calculation, when our computer checks the condition and it becomes false, the loop will stop and this call will not be made. The intersection call will not be made. Now again, return the x and y values after all of the things that we have done. And as you can see here, let me make a force-added polygon. So here as you can see the x coordinate. So here we are using the tuple unpacking method because our function is returning a tuple. So we are unpacking the tuple in these variables x coordinate, y coordinate, and sides. So this is how it is done. Now here is the cleaning part that I've just told you. As I just told you that if you do not clean the x coordinate and the y coordinate, then it will become just oscillating, bridged between that -1 point, because the -1 point, this point -1 point, it will become again, it will come again and again, and which will hinder the creation of creation of our regular polygon. So we'll discuss this, but let's see how our code will look. So here is our here's our plot. This is our square that we have made. So if what would happen if you will not do the cleaning part is that it will go from here to here, again it will come here, then it will go here onto the second intersection point, then again it will come onto this side, again then it will go to this side, the last intersection point, then again it will come back to come back to the first point. So that's why the cleaning part is very necessary. We'll have to remove these alternating -1 values from our x-axis as well as from the y-axis. So from y-axis we have to remove 0. So the coordinates corresponding to this point from where we are starting is -1, 0. So just like -1 is repeating again and again in our x coordinate list, 0 corresponding to the y coordinate of this point, the first point, 0 will repeat again and again in our y coordinate list. So we'll have to if you didn't got that, let's discuss that as well in on a separate slide, on a separate in our whiteboard. So So for this point, our coordinates are -1 comma 0, right? So if this point is so if minus 1 the so if the -1 point is incremented again and again in our x coordinate list, this 0 point will be incremented again and again in our y coordinate list, right? So so that is why we have to clean both the x and y coordinates. Okay. Yeah. So I have made another list. So let's discuss the last cleaning and arranging part. So I made another list called the clean x coordinate and the clean y coordinate, and obviously I'll use a loop, and the loop will run along the length of the x coordinate, because obviously the amount of at max the loop can run to the amount of numbers that you have in your amount of coordinates that you have, the amount of x coordinates that you have in your x loop, right? It doesn't matter if you use x or y, whatever, because both of them will be having the same amount of numbers. So here what I'm doing is because the loop, the for loop, or the range object gives out the so the range function gives out the range object, and the range object, if you'll not specify the initial position, then it starts counting from 0 to whatever number you provide, right? So and the indices for our list as well starts from 0. So what we are doing in this case is if the if for if at any value in the if at any value in the x coordinate, the only append those values which are not equal to 1. This is what this line is saying. Do not append any value which is equal to -1. So if at the ith index the value is not equal to -1, then append that ith index value into our clean x coordinate. But if the I is equals to 0, that is we are talking about the first element. So the first element is actually part of our vertex, right? This I know that all of the other times that we get -1 comma 0, that won't be part of our vertex. But in the first case itself, this is the common vertex for all of our polygon, right? So in the very initial -1, the very initial -1 is actually part of our vertex, so we won't discard that. Okay. Yeah, so we won't discard that. So that's what I'm saying, that if the ith value is 0, then append that -1, because in our first value is will obviously be -1, right? So append that first -1, but apart from that first -1, do not append any -1. This is what the first loop is saying. Now the second loop is actually interesting, because the first part is quite similar, because here you can see that I'm mentioning that append all the values which are non-zero. If any value is 0, then do not append that value. But here, as you can see, I have defined some additional conditions. Now what I will do is I will discuss those conditions first, then I will discuss the code. So let's imagine a case. So just like -1 in case of in the case of x coordinate, we are removing zeros, which is obviously the y coordinate of -1, right? But there's also one case where the y coordinate is 0. There's also one more case where the y coordinate is 0. Now what may happen is that what may happen is that, let's say for any polygon, you are on this particular um, you're on this particular, so we will focus on the y coordinates only. You're in this particular point, which is nothing but a comma b. So what will happen in the y coordinate is that for this b will be b will be appended. Then after after the calculation of this intersection point, the rotation will be made. Again we'll go to the 0 point, and let's say after the rotation the line becomes horizontal. The line becomes horizontal. Okay, the line becomes horizontal. And after this, let me make some space here as well. Yeah, so after this rotation you will start from -1 again, and corresponding to -1 you'll get 0 as your next value, right? But you know that after the incrementation process is done over this line, just like this, after the incrementation process is done, the next intersection point is found on this side, right, on the other side of your unit circle. So the y coordinate for that unit circle of the y coordinate for that point is also 0, right? Again the rotation will be made, and you will get some other line. And for that line also you'll start from -1 comma 0, and again the 0 of the y coordinate of this for this particular point will also be implemented, will also be appended like this. So as you can see that when you first got to the horizontal line, this 0 was appended, right? Then the 0 was appended as part of the first point. Again after the incrementation was done, after the intersection point calculation was done, because it was a horizontal line, it intersected the circle at the other end, so 0 was again implemented, because this point is 1 comma 0. So in the y coordinate list 0 was again implemented, I'm sorry, appended. And after again the rotation was done, and in that rotation again we'll start from this point. The initial point is same for all, as you know that the initial point is same for all. So because the initial point is same for all, the -1 will be appended in the x coordinate list, and 0 will be appended in the y coordinate list. 0 will be appended in the y coordinate list, as you 0 will be appended in the y coordinate list. So as you can see, 3 zeros have come in a kind of group in this particular case, and this will always happen if there is a horizontal line in the picture. For example, in case of square it will definitely happen, right? As you know that it will become like this. The square is like this. So there is a horizontal line involved. As you can see, there is a horizontal line involved for the calculation of this intersection point. There's a horizontal line involved. So in case of a square, we'll encounter this problem, but 3 zeros will come in group, and what will happen is that in the corresponding x coordinate, what will happen? You'll have a for this line, for this point, then you will have -1, then you will have 1, and then you will have again so 1 -1 and again -1, right? So after this rotation, -1 will be appended to the x coordinate list, and after incrementation and calculation of intersection, 1 will be appended, and rotation will be made, and again -1 will be amended. So what will happen in the process of x cleaning is that these two values will be discarded, right? You must be knowing that the length of x coordinate at the length of x coordinate is equals to the length of y coordinate, right? Both of them have the same amount of so yeah, both of them have the same amount of values, both of them have the same amount of items, both of them have the same amount of elements. So the length of x coordinate and the length of y coordinate will be same. So the length of both the lists will be same. So due to our x coordinate cleaning procedure, these two values will be discarded, the -1 and the -1. Now because we will be performing our cleaning on y as well, and we are discarding all the zeros corresponding to -1 comma 0, this 0 which is actually needed corresponding to this 1 will also be discarded if we just apply the procedure of cleaning blindly. All of these values will be discarded, and actually the balance will be disturbed, because here we have one value of x corresponding to which the y value has been discarded. 1 comma 0 is the coordinate that we are looking for, because this coordinate is needed, right? In case of square, this coordinate is needed. This is one of the vertices of our square. So for a particular coordinate, we have the x coordinate. For a particular coordinate, the x the abscissa or the x coordinate is intact, but the y coordinate has been discarded, and therefore the length, the balance of length of the lists are disturbed, because you will have one value in the x coordinate corresponding to which the y value will not be present, right? The zero will be lost. Therefore we have to take this nuance into account, especially because of which you found that I have written some extra bit of code in the cleaning of y coordinate. Now there's one more thing that might happen, which may give us an error. Let's say we after all of these things, if we get to the last bit of our list, right? So the second last item, let's say it's C, K, P, something like that. So if we are using indices for judging whether 3 zeros are present or not simultaneously, then the zeros could be present here as well. I mean, that means it actually what will happen is that if you are checking if 3 zeros are present, simultaneously or not, actually what we have to do is that we have to append one of the zeros from the group of 3, right? So that this pair can remain intact, so that one of the zeros can go and pair up with the one that is left here in the surrounded by 2 -1s. So if we are using index for that, if we are using index for finding out whether 3 zeros are not present, for example, if we get to an index I, then we'll check that if I plus 1, that is, let me use another color, some bright color would be better. So if we are at any index I, we'll check if I plus 1 has the 0 or not, and I plus 2 has the 0 or not. If all of these three indices, if the value corresponding to all of these three indices is equals to 0, x of I, y of I plus 1 and y of I plus 2, if values corresponding to all of the three indices, I plus 1, I plus 2, corresponding to all of the three indices are 0, then we will have to implement one of the zeros, right? One of the zeros from the group of 3. So the condition will be like this: if the ith index of the y coordinate list is equals to 0, and the I plus 1th index of the y coordinate equals 0, and the I plus 2th index of the y coordinate, the value corresponding to I plus 2th index is equals to 0, then we'll have to append one value, append 0, right? So the problem in this code is the moment our loop will hit the last parts of our code, that is the CKP part, the last part, that is what that is what we have here, the CKP part. If it hits the last part of our code, let's say it hits the C part, so it will check for I, which is C, I plus 1, which is K, I plus 2, which, so ith part, which is C, I plus 1th part, which is K, and I plus 2th part, which is P. If we encounter if this condition is checked, on this point, then our interpreter, the Python compiler interpreter, won't have any problem. But at this point, if it comes to K, then y of I is K, y of I plus 1 is P, but y of I plus 2 is not defined. And here the Python interpreter will throw us an error that the index will, the thing that we are trying to access does not exist. The index, the value corresponding to the index does not exist, and in case of P, it would create even more problem, as y of I is P, but y of I plus 1 and y of I plus 2 is not defined. Therefore we have to check this particular case up and until we get to this point. For these three cases, or maybe for the last two, because even if for this case we won't face any problem, but for the last two cases, or for the last two values, we want that we don't want to check this particular condition. And obviously there's no polygon that I've heard of which will stop in the semicircle, right? The polygon obviously will go beyond the semicircle and cover the whole circle, right? So it will never happen that you are on a horizontal line and you are at the end of your y coordinate list. So we have to check, we have to exclude the so what we have to do is we have to exclude the condition checking for the last two values of y coordinate. So let's go and see how I have implemented this thing. So so the first condition is very easy to see, that y of I is not, so implement all the y of i's which is not equal to 0. So I'm excluding all the zeros from my list. But here is what so the first condition that I've applied is if the I is not, so this condition will only, so this part of code will only run if these two conditions are satisfied. That is, whatever I am at, it is not the length of the y coordinate minus 1, because you know that the length of the y coordinate starts, obviously the length calculation starts from 1 to whatever n, the length of whatever the length of our y coordinate, the length of our list, the calculation of length starts from 1, right? But the indices, they start from 0. So whatever the length of my y coordinate is, minus 1 will give me the index, right? Length will give me a value which might not even be an index, right? So in in a list where we have 5 elements, the indices will only run from 0 to 4, right? So that's what I'm doing. I'm excluding the application of these two conditions for these two indices. The length of y coordinate -1, this is the last index of our y coordinate list, and length of y coordinate -2 is the second last index of our y coordinate. Because if you'll see, if you have a list of 5 elements, then the index run from 0 to 4. 5 is the length, -1, which is 4, is the last index. So n minus 1 will be your last index, and n minus 2 will be your second last index. So for these two indices, I am excluding the application of this condition. And what condition I'm applying? The condition that we discussed in the whiteboard. If y of I is equals to 0, along with that, if y of I plus 1 is equals to 0, and along with that, if y of I plus 2 is equals to 0, then append one of the zeros, that is append the y of I 0. Okay, so we are not appending all of the zeros, but some of the specific zeros. So this is a very fine nuance that we have here, right? That we are applying here. This is a very fine detailing that many people would miss, as I missed in my first try as well. So I had to figure it out, that where the problem is lying, and this was the problem. So here it is, and then this is the only this particular bit is only applicable to the y coordinate. Rest, I is equals to 0 for the first coordinate. Obviously, for the first for our first coordinate, in both our x and y, we are having -1 and zeros, right? So for I is equals to 0, we have -1, and for I is equals to 0, we have 0. In our y coordinate, we are having 0, and in our x coordinate, we are having -1 for the first index, right? Because the first index is common to all of our polygons. So the -1, 0 will be there for the first index, for the first coordinate. And we don't want -1, 0 for the rest of our list appearing on an alternate basis. That is not we want. That is not what we want, right? So this is what it is. This is the condition that we have applied here, that if 3 zeros come in a group, then append one of the zeros. Append the 0 at the ith position, and if we get to the I plus 1th position, then only two zeros will be, as you can see here, that if we come to this particular position, if we come to this position, then only two zeros will be in a group, and for that we don't have to do anything. Both of the zeros will be discarded. We don't need those zeros. We only need we only need a 0 to pair it up with the 1 that we have in our x coordinate list, right? So that is what we will not discard. So this is what we are appending as well in this case. Yeah. So the first and in the 0th index, we are having -1 in the x coordinate, and in the 0th index we are having 0 in the y coordinate, right? The common vertex for all of our polygons, the first vertex for all of our polygons. Now, why I am adding a final segment as well? Why am I adding the final segment -1, 0 as well to our list? Now, what will happen is that after it hit, so what will happen is that, so after it hits the last side of our polygon, we will only get this intersection point. Now, to connect this intersection point, the last intersection point, with the first point that we have, because obviously a polygon is a closed loop, right? So it starts from some point and it ends at the same point, but we won't be getting this point -1, 0 from our intersection. So we'll have to add this final segment, so to connect the initial position from where we started to the final position that we got, right, to the final position that we, the final intersection point or the final position that we got from our function. That's why I'm adding the final segment of -1 comma 0 to connect these two points. So this is what it is. Final segment equals to -1 and final segment. So I could have appended this directly, append -1 and append 0, but this looks a bit neat, and it kind of self-explains that what is happening. I'm adding the final segment because a regular polygon or any polygon is a closed loop, so it starts from the same point where it ends. So in this case, as you can see, that that we will not be getting -1 comma 0 at last, the point where we started, right? So we have to append -1 and 0 at the very last position, so to complete that polygon. Otherwise that last segment won't be made, and we'll be only left with the intersection point and the first point separated by some distance like this. If I'll not add this final segment, then our square will look something like this. Our square will look something like this. It'll go here. It is not at all looking like a square. Yeah, these 2 points won't get connected if I don't add the final segment coordinate. The matplotlib won't connect these 2 points by itself. So to connect these 2 points, we'll have to add the final segment of -1 comma 0, the final coordinate, the coordinate from where it got started in the first place, right? So this is what it is. And there's nothing more to discuss after that. This is the plot that I have made. If you know the basics of matplotlib, the thing that I wanted to focus on is the mathematics and the logic behind writing a polygon inside a unit circle in Python and matplotlib. And I won't be focusing on obviously. So I don't have much interest in focusing all these things, that how I have drawn a this is the code in matplotlib for drawing a horizontal line, AXH line, which means axis horizontal line. AXV lines means axis vertical line, defining the limits, and then plotting the circle np cos theta, np sin theta, and then we just have to supply the cleaned x coordinate and the cleaned y coordinate in the plot functionality of matplotlib, and it will draw the polygon itself. So what it does is, if you supply it with the coordinates, it just joins all the coordinates with a line. So that is the reason why we have calculated only the vertices, only the intersection points of our regular polygon, or only the vertices of our regular polygon, and rest is done by matplotlib to connect all the vertices by a straight line. So the plot functionality does that by itself, connect all the vertices by the straight line. Okay, so so here I'm cleaning. So here I'm adding the cleaned x coordinate. This the list that I have made after all the after appending all of the values, after cleaning all of the values and appending all of the values. Cleaned x coordinate append, clean y coordinate append. And this particular functionality only works when we have sides greater than 0. So what it does is, because when you make the sides even greater and greater, the broad perspective, it just dilutes the polygon actually, because the polygon starts to take the shape of the circle itself, right? This is what I have discussed in my which video I have just yes, in my integration and differentiation video. I used this this particular simulation to show you that as you increase the number of sides, the polygon starts to become a circle itself. So you can say that the circle is nothing but a polygon of infinite sides. Yeah, you may say that. You may define a circle like the polygon of infinite sides, because as the sides of the circle increases, it approaches as the size of as the sides of the polygon increase, it starts to become the circle itself. So that if you want a much more detailed theoretical reason behind why it happens and what happens, then you may watch my integration and differentiation video that I've uploaded on my YouTube channel. It is called the perspective differentiation and integration. So when the sides become greater than 16, then there's a subplot that is. So I am using the subplot functionality of matplotlib to create two plots side by side. And the other plot is actually a zoomed version. As you can see that the other plot is very, very zoomed, very to show you actually the nuance, to show you actually the nuance and the difference between the side and the between the polygon, to show you actually the difference between the polygon and the circle, because from a very broad point of view you won't see any difference. If you want to see that, then let me show you that. If I increase the number of sides to, let's say, 47, so let my computer calculate the coordinates for all of my so these are all the coordinates, the x coordinates, and these are all the y coordinates. As you can see, the list is very long. So this is what it is. As you can see that in this particular case, you cannot even distinguish between the polygon and the circle. But in this case, you can see that there's a very fine distinguish. So the nuance is actually very fine between the polygon and the circle. So that's why I have made this subplot function if the sides if the sides are greater than 16. But that is not what we were discussing in this video. Our main discussion was to make a regular polygon inside a unit circle, and that's what we have done. And let's end this video. This video has got this video particularly has gotten very lengthy, which I never wanted, but just for the sake of explanation in depth, I took my time. So thank you so much for watching, and I'll see you in the next one.